Hi, I am Raghavan, Chemistry faculty from All Foods College. I invite you all for the All Foods Chemistry e-learning classes. Okay, session 30. So in the last session we have started the concept of orbitals. So in the last session we completed the concept of s orbital. Now in this 30th session, let us take up the concept of p orbital. The concept of p orbital. Okay, what is a p orbital? How we can designate that p orbital or p subshell? That is, the subshell with L is equals to 0. The subshell with L is equals to 0 is designated as p subshell. Is designated as p subshell. Okay, and the number of orientations, the number of orientations, the number of orientations, the orientation values, orientation values, orientation values, that means m values, orientation values of this subshell, when L is equals to 1, that is azimuthal quantum number value is 1 for the p orbital. Okay, for p subshell L is equals to 1, then now the orientation values are from -1, 0 and +1. Okay, the orientation, that is azimuthal quantum number value is 1, that is designated as p subshell, and the possible orientation values are -1, 0 and +1. The number of orientations, now the next point is the number of orientations, The number of orientations indicates what? Number of orientations, that means number of orbitals. Number of orbitals. That is equals to, as we know that, 2L plus 1. Okay. Now 2L plus 1 means 2 into L is equals to 1. So 2L plus 1, that is equals to 3. This indicates what? Any p subshell contains 3 p orbitals. Okay, that is the point we understood. Now clearly let us write any p subshell contains, any p subshell has 3 p orbitals. 3 p orbitals. Yes, 3 p orbitals. Okay, any p subshell, it may be 2p, 3p, 4p, whatever it is, any p subshell contains 3 p orbitals because it has the total number of orientation values are equal to 3. Okay, so any p subshell contains 3 p orbitals. Okay, that is the concept we understood. Now the number of nodal planes, next point is number of nodal planes. Number of nodal planes is equals to 1 because number of nodal planes equal to L value. So because L is equals to 1, therefore the number of nodal planes are equal to 1. Okay. So once again, what is a p orbital? The subshell with L is equals to 1 is designated as p subshell, and the orientation values of this L is equals to 1. The possible orientation values are equal to -1 to +1, including the 0. The total number of orientation values indicates the number of orbitals in the subshell, that is 2L plus 1. That means this p subshell contains 3 p orbitals. Okay. Now the number of nodal planes equal to 1 because L is equals to 1. Because L is equals to 1. Yes, this is just general introduction about p orbital. What is the shape of the p orbital? And we can say, yes, the shape of the p orbital is dumbbell shape. Yes, dumbbell, or you can say, you can write dumbbell. Okay, dumbbell shape p orbital. Okay, having, what is a dumbbell shape p orbital? Let us say like this, dumbbell shaped p orbital. This is the dumbbell shaped p orbital. This is the dumbbell shaped p orbital where we have, this is a dumbbell shape, and in this we have the probability of finding electron is more, so that is called lobe. Okay, so this is one lobe, this is another lobe. That means the dumbbell shaped p orbital has two lobes. What is the meaning of lobe? The lobe is the space around the nucleus where the electron density is maximum. Electron density is maximum, that is called lobe. Electron density is maximum, or you can say the probability of finding electron is maximum, that is called lobe. So the p orbital has dumbbell shape and it possesses two lobes. Okay, two lobes are there. It is two lobes and one nodal plane. Number of nodal plane is 1. Dumbbell shaped p orbital has two lobes and one nodal plane. Okay, that is a theoretical information about p orbital. Okay, now let us draw the shapes of the p orbitals. Draw the shapes of the p orbitals. Okay, that is diagrammatic explanation of the p orbital. Right. How many orientation values are possible for p orbital? Yes, the p subshell has 3 orientation values, that is magnetic quantum number values, that is m is equals to, we already explained that -1, 0 and +1. Okay, based on the 3 orientations we can say that the p subshell contains 3 p orbitals. Okay, what are the 3 p orbitals? Yes, this p subshell contains 3 p orbitals. Yes, one is px orbital, second one is py orbital, and third one is pz orbital. The 3 p orbitals. And remember the important point, that is conventionally the orientation value for pz orbital is 0. Conventionally the orientation value for pz orbital is 0. That means px and py you can represent -1 and +1. So remember that. So we used to write regularly -1, 0, +1. Okay, but conventionally the pz orbital orientation value is 0. That we have to remember. So how many p orbitals are there? 3 p orbitals, px, py, pz. Okay, now let us draw the diagrams of these p orbitals. Okay, first let us take up px orbital. What is px orbital? Px. Next let us take up py orbital and then pz orbital. Okay, right. The px orbital in which the two lobes are oriented along the x-axis. The px orbital, the p orbital in which the two lobes are oriented along x-axis. The two lobes are oriented along x-axis. The p orbital in which the two lobes are oriented along the x-axis, that means the probability of electron is maximum along the x-axis. That is called px orbital. Okay, so px orbital. Now here it is y-axis and z-axis. Now when the electron density is maximum only on the x-axis, so therefore, so that is yz plane is the nodal plane. Yz plane is the nodal plane for that. Yz plane is the nodal plane. Okay, that we can draw with a different color. So yz plane is the nodal plane. Yz is nodal plane. Yes. Next, py orbital. The p orbital in which the two lobes are oriented along the y-axis. The two lobes are oriented along the y-axis. The two lobes are oriented along the y-axis. Yes. The two lobes are oriented along the y-axis is called py orbital. So this is the py orbital. The two lobes are oriented along the y-axis. Then zx is the nodal plane for that. Zx orbital is the nodal plane. Zx is nodal plane. Nodal plane for py orbital. Next, pz orbital. Pz orbital. Okay, in this pz orbital, the two lobes are oriented along the z-axis. The two lobes are oriented along the z-axis is called pz orbital. The two lobes are oriented along the z-axis is called pz orbital. So when it is a z-axis, so automatically we can understand that xy plane is the nodal plane. Xy plane is the nodal plane for that. Xy plane is the nodal plane because the z-axis is like this, x-axis, y-axis and z-axis. So automatically when the lobes are oriented along the z-axis, so xy plane will be the nodal plane for that. Okay, this is the diagrammatic explanation of the p orbitals. Okay, once again, the p orbitals. What is a p orbital? The subshell with L is equals to 1 is represented as a p subshell, and the possible orientation values for this L is equals to 1. So m values are -1, 0 and +1. The total number of orientations for this subshell, that is 2L plus 1, that is 2 into 1 plus 1, that is equals to 3. That indicates what? Any p subshell contains 3 p orbitals. Any p subshell contains 3 p orbitals. Okay, what are the 3 p orbitals? We have px, py and pz orbitals. Okay, we have 3 p orbitals, right? Now, what is the shape of each p orbital? P orbital has a dumbbell shaped structure. Okay, dumbbell shaped structure, that means it contains 2 lobes. Okay, as earlier we have shown in the diagram, that is 2 lobes are there. Okay, 2 lobes and 1 nodal plane. How you can say that 1 nodal plane? Because L value is equals to 1. So that is p subshell, that is p orbital having 2 lobes and 1 nodal plane. Okay, now as per the 3 p orbitals, px, py, pz, now the diagrammatic explanation like this. So in px orbital what happens? The 2 lobes are oriented along the x-axis. Okay, so 2 lobes, that means the electron density is maximum along the x-axis. Then yz plane, we can consider it as nodal plane for px orbital. Then py orbital. In this py orbital, we have the 2 lobes are oriented along the y-axis. That means, so zx plane is the nodal plane. Zx plane is the nodal plane for the py orbital. Next for pz orbital, that means the 2 lobes are oriented along the z-axis. So xy plane is the nodal plane for pz orbital. Okay, this is about p orbitals. Okay, p orbitals. What is the nodal plane for this? Xy plane. Xy plane is nodal plane. Nodal plane for pz orbital. Okay, so this is diagrammatic explanation of px, py, pz. Okay, next we are proceeding to the radial probability distribution curve for the p orbitals. Okay, radial probability distribution curve for the p orbitals, right? So remember, how many nodal planes are possible? Sir, number of nodal planes always equal to L value. We should not forget. Okay, number of nodal planes always equal to L value, right? Next, coming to the radial probability distribution curve for the p orbital. Yes. What is the shape of the p orbital? The shape of the p orbital is always, it is a dumbbell shaped structure. Okay. Now, the radial probability distribution curve for the p orbital. Let us radial probability distribution curve for the p orbitals. Let us understand. It is a dumbbell shaped p orbital. So let us draw the dumbbell like this. First dumbbell, that is, say it is 2p orbital. It is 2p orbital, right? So 2p orbital, this is 2p orbital. Next, let us have one more dumbbell, that is 3p orbital. Now the 3p orbital, the size of the 3p orbital is bigger than the 2p orbital. The size of the 3p orbital is bigger than the 2p orbital. Yes. The size of the 3p orbital is bigger than the 2p orbital. And let us write one more, that is 2p, 3p, then 4p orbital. That is little more bigger than the 3p orbital dumbbell. Because every p orbital has a dumbbell structure only. Okay, now let us label it. So this is 2p orbital, and it is 3p orbital, and it is 4p orbital. Okay. Now, when you plot a graph between, that is radial probability, and this is d function, that is radial probability, that is 4 pi r square dr psi square versus the radial distance from the nucleus. So the 2p orbital is having one peak. This indicates 2p orbital. Okay, then 3p orbital is bit higher, and 3p, then next 4p orbital is still higher. So this is 2p, this is 3p orbital, and this is 4p orbital. 4p orbital. So they have the structures like this. Okay, and this one, this space is called, this is first peak, then it is second peak, then it is third peak. Okay, this point is called node or radial node. Number of radial nodes. Number of radial nodes. Number of radial nodes equal to n minus L minus 1. So now we have 3 p orbitals we have taken. So 2p orbital, number of radial nodes, n minus L minus 1. N is equals to 2. L value for p orbital 1 and 1. That is equals to 0. For 2p orbital there is no radial node. See, what are the radial nodes we have? Radial node, you can call it radial node or node or nodal surface or spherical nodes. Okay, they are all same. Right. Now for 3p orbital, we have one node. Okay, for 3p orbital we have one node. Let us write here. So 3 minus 1 minus 1, because n minus L minus 1. N is equals to 3. L value for p orbital is 1. So minus 1, that is equals to 1. Next for 4p orbital, okay, so for 4p orbital we have two nodes are there. So now 2p, 3p and 4p, that is equals to, 4p is equals to 4 minus L value 1 minus 1, that is equals to 2. So these are the two for the 4p orbital. This is about number of radial nodes. Okay, number of radial nodes equal to like this. Number of radial nodes. Okay, next, what are the angular nodes for them? Angular nodes are nothing but number of nodal planes. Okay, number of angular nodes. Let us write the concept here. Number of angular nodes. Number of angular nodes equal to L value. Number of angular nodes always equal to L value. So now you can say, so number of angular nodes for 2p orbital, 3p orbital and 4p orbital. Yes, it is always equal to L value. See, for any p orbital, L value is always equal to 1, isn't it? For any p orbital, L value is always equal to 1. Therefore, the number of angular nodes always equal to 1 for all of them. Okay, is it the concept is clear? The very important concept and very interesting also, but you should more concentrate on this to understand. Okay, so this is about radial probability distribution curve for the p orbitals. Okay, so 2p orbital, 3p orbital, 4p orbital, and you can also add one more point. See, we have 3 different orbitals are there, and what is the energy of these p orbitals? And remember, according to Bohr's theory, we learned that is, as n value increases, that means as the orbit number increases, as n value increases, the energy of the orbital also increases. Energy increases. That means energy of the 2p orbital is less than 3p, 3p less than 4p. That means now we can say, we can add one more point, energy of 3p orbitals, that is 2p orbital energy less than 3p, 3p energy less than 4p. Okay, that is also additional point we can add. Okay, so we completed all the points which are very important for all the competitive examinations like EAMCET examination, mains examination also. Okay, and it is very much useful for all your objective examinations. Don't forget, because we explained the concept with the diagrams and all the important data is also mentioned. The important data is always mentioned in the boxes. Okay, so that is why you should not forget, while writing the notes also, you keep the important points in the box so that you cannot forget it. Okay, that is very important point you should learn. Right. So the p orbital concept is now completed. Now we are moving into the d orbital, the concept of the d orbital. Yes, The concept of d orbital. Okay, we completed, in the last session we completed the concept of the s orbital, and we have started the p orbital introduction there itself, but today we have taken the concept of the complete p orbital along with the previous introduction also. Okay, so that is p orbital is now totally completed. Now we are moving to the d orbital, concept of d orbital. What is d orbital? Yes, the first point is the concept of d orbital is the subshell with L is equals to 2. The subshell with L is equals to 2 is designated as d subshell. Yes, the possible orientation values for this L is equals to 2. The orientation values, that means magnetic quantum number values. Okay, m values, let us say m values. Okay, that is equals to -2, -1, 0, +1 and +2. Total how many values are possible? Count it. 1, 2, 3, 4 and 5. Yes. So that means the subshell with L is equals to 2 has 5 orientation values. That means that subshell contains, each value represents one orbital. We know that. So 5 values are there. Therefore, the subshell with L is equals to 2, that is d subshell, it contains 5 d orbitals. Okay, that is the total number of orientation values are equal to 2L plus 1. Yes, apply that. That is equals to 2 into L value is 2 plus 1, that is equals to 5. Yes, the d subshell contains 5 d orbitals. Yes, the d subshell contains 5 d orbitals. Yes, what are the designations of them? Let us see. 5 d orbitals, 1, 2, 3, 4 and 5. Yes, 5 d orbitals we have. The designations of these 5 d orbitals like this. One is dxy, dyz, dzx and dx square minus y square, and last is dz square. Okay, what are the designations of the 5 d orbitals? dxy, dyz, dzx, dx square minus y square and dz square orbital. Okay, so there are 5 d orbitals are possible. Okay, now what are the orientation values for these d orbitals? Okay, and remember one important point, like p orbitals, conventionally the orientation value for dz square orbital is always 0. That means it is -2, it is -1, +1 and it is +2. Conventionally, the dz square orientation value is 0. Okay, we should not forget that, it is important, right? So this is about what is a d orbital and how many d orbitals are there and what are their orientation values. Okay, that is a representation of the d orbital. Now coming to the, what is the shape of the d orbital? Shape of the d orbital is, it has a double dumbbell structure. It has double dumbbell structure. The shape of the d orbital is double dumbbell structure. That means it has 2 dumbbells. Okay, this is one dumbbell form. Next, another dumbbell we can draw like this. This is another dumbbell form. It has double dumbbell structure. For each dumbbell we can find out one nodal plane. So now in this double dumbbell structure, next point is number of nodal planes. How many nodal planes are present? Sir, number of nodal planes always equal to L value, that we know very well. So number of nodal planes for the d orbital, L value is equals to 2. Therefore, the number of nodal planes are always equal to 2. Yes. Okay. Number of nodal planes are 2. Right? How many lobes are present? Sir, each dumbbell we have 2 lobes. Okay. And 2 dumbbells are there. Double dumbbell. That means total we have 4 lobes. Number of lobes is equals to 4. 2 nodal planes are present and 4 lobes. Okay, it is a double dumbbell orbital. Okay, right. So how many d orbitals are there? So total d orbitals are 5. The designations of the d orbitals we have given clearly, right? Next we have to move towards the diagrammatic explanation of the 5d orbitals. Okay, let us go to the 5d orbitals, the diagrammatic explanation of the 5d orbitals. 5d orbitals, yes. What is the L value for the d orbital? That is, the subshell with L is equals to 2 is designated as a d subshell. Okay, the subshell with L is equals to 2 is designated as a d subshell. Okay, L is equals to 2 is designated as d subshell. Suppose if the d subshell is present in third orbit, n is equals to 3, that is designated as 3d orbital. Okay, don't forget that. That you can explain that 3d, 4d, 5d, 6d like that. So it based on the n and L values. Okay, right. Now 5d orbitals we have. First, now let us write in the first 3d orbital, that is in dxy, dyz and dzx orbitals, in dxy, dyz and dzx orbitals, the four lobes are oriented. Four lobes are oriented between xyz axis. Four lobes are oriented between xyz axis. Okay, between xyz axis at an angle of 45 degrees. Okay, that is very important point. That is the first point we should remember. So what is it concept? In dxy, dyz, dzx orbitals, in these 3d orbitals, the four lobes are oriented, means they are present. Lobe means what? Electron density. Okay, the electron density is present, oriented between, not along the axis, remember, between xyz axis at an angle of 45 degrees. Okay, let us write that. So now say it is x-axis, say it is y-axis, and assume it is a z-axis. Okay, it is z-axis, right? Now in this, the four lobes are oriented between xyz axis, okay. So that is, the lobe is between, yes, between the axis, yes. Next it is dxy, okay, it is dx and y. The lobes are oriented between xyz axis only, xyz axis. The lobes are oriented between xyz axis, like this. Okay. Now, what is the angle between the axis? Between the axis angle is total, it is 90 degrees. From here to here it is 90 degrees. So, what is the position of the electron density? Electron density is oriented exactly at 45 degrees. So, that is, the orientation of the electron density, electron cloud in between the axis is 45 degrees. Very important point, you should not forget it. Okay, I repeat once again. In dxy, dyz and dzx d orbitals, the four lobes are oriented between xyz axis at an angle of 45 degrees. Okay, not along the axis. They are oriented between xyz axis. So therefore, the angle between the xyz axis exactly, the electron density is found at 45 degrees. Okay, let us take another one. Okay, x, y and z. The lobes are oriented between, it is between the axis we have to draw, not along the axis. Okay. between the axis. We can put the electron density between the axis. Okay, that is dxy, dyz, dyz. Okay, for all these three, you can write the same diagrammatic representation, because as usual, the electron density is not along the axis, they are in between the axis. Okay, that is in between x, y, z axis. Okay, that is dxy, dyz and dzx orbitals. So the lobes are oriented between x, y, z axis. I mean, coming to the next one is, so that is second. So that is, we have one more, that is dx square y square orbital, dx square y square orbital, in which the four lobes are oriented, along x and y axis. Four lobes are oriented along x and y axis. Four lobes are oriented along x and y axis. Okay, the lobes are oriented along x and y axis. The four lobes are oriented along x and y axis. Remember this point. In this, the lobes are oriented along x and y axis, along the axis. Okay, and coming to the last one is dz square orbital. In this dz square orbital, okay, the lobes are oriented along the z-axis. Be careful, it is very interesting and important point. Okay, the dz square orbital, it is a peculiar orbital in which only two lobes are oriented along the z-axis. Only two lobes are oriented along the z-axis. Okay, only two lobes are oriented along the z-axis. Okay, and the remaining two lobes forms like a ring around the z-axis. The remaining two lobes forms like a ring-like structure around the z-axis. This ring-like structure is called a torus. The torus structure, that indicates torus structure. So we had the complete diagrammatic explanation of the 5d orbitals. Okay, in the first 3d orbitals, the lobes are oriented between x, y, z axis. And in dx square minus y square orbital, the lobes are oriented along x and y axis, whereas in dz square orbital, only two lobes are oriented along the z axis, and the remaining electron density forms like a ring-like structure around the z axis. This ring-like structure is called torus arrangement. Okay.